Welcome back. You may have seen the movie Matrix. There's a concept in it that resonates with me. We often accept reality as it's shown or explained to us. But I believe a free mind thinks differently. It doesn't just follow rules, it creates them. And on this channel, we embrace new perspectives and fresh ideas. In today's video, we'll dive into something revolutionary, a new type of geometry that I call dimensional geometry. We'll begin by revisiting traditional geometry and then explore how this new approach can redefine how we think about space, angles, and dimensions. Let's start with a quick recap of traditional geometry. In two-dimensional geometry, an angle is defined as the space between two lines. For example, as you see on the screen, we measure the angle between two intersecting lines. Trigonometry plays a key role here. Sine theta is equal to the width divided by the hypotenuse. Cosine theta is equal to the base divided by the hypotenuse. We also have the well-known Pythagorean Theorem, which states the square of x plus the square of y is equal to the square of r, where r represents the hypotenuse. When we divide the entire equation by the square of r, we get the following. The square of sine theta plus the square of cosine theta is equal to 1. This is a foundational concept in traditional geometry that you're probably familiar with. Now here's something to think about. Why do we use two-dimensional geometry principles in three-dimensional spaces? In three-dimensional geometry, we still measure angles between two lines, just as in two-dimensional geometry. Isn't that strange? This is where dimensional geometry comes in. It challenges these conventions and suggests a new way of thinking. Dimensional geometry proposes that each dimension has its own unique geometry. For example, in three-dimensional geometry, an angle would not just be defined between two lines. Instead, it would be defined between three lines simultaneously, just as angles in two dimensions are defined between two lines. If we extend the Pythagorean theorem into three dimensions under this framework, it might look like this. The cube of x plus the cube of y plus the cube of z is equal to the cube of r. At first glance, this may seem unconventional, but if the angle is measured between three lines at the same time, this equation could make sense. Here's something even more exciting. In traditional geometry, we use sine theta and cosine theta. Sine theta is equal to the width divided by the hypotenuse. Cosine theta is equal to the base divided by the hypotenuse. In dimensional geometry, I'm introducing a new trigonometric function. Caf theta is equal to the height divided by the hypotenuse. If we apply this to the three-dimensional Pythagorean equation and divide by the cube of r, we get the following. The cube of sine theta plus the cube of cosine. Theta plus the cube of caf theta is equal to 1. This equation suggests that caf theta plays a critical role in understanding three-dimensional spaces. While this isn't proven yet, it opens the door to new possibilities, including using caf theta to explore odd zeta functions, much like Euler used sine theta and cosine theta for even zeta values. Dimensional geometry encourages us to think beyond the limitations of traditional geometry. By redefining angles and introducing new concepts like caf theta, we can explore dimensions in a whole new way. What are your thoughts on this approach? Could caf theta and dimensional geometry help us unlock new mathematical insights? Let me know in the comments below.